A human face is never static. It is a dynamic, shifting topology where shadows, lighting, and microexpressions are constantly altering the physical surface. But a computer doesn't see a cheekbone or a smile. It sees a grid of raw, independent pixels, each assigned a specific numerical value. This creates an immediate problem for machine recognition. Take two photographs of the exact same person, snapped just seconds apart. To a human, they are identical, but to a computer comparing them pixel by pixel, a slight change in the room's lighting or a one-pixel shift to the left registers as a massive mathematical error. That comparison is incredibly heavy. A dataset of 400 standard resolution images is processed as a matrix with over 65,000 dimensions per photo. Running calculations across 65,000 separate dimensions for a single image comparison is computationally expensive and logically flawed. Standard pixel space distance metrics fail here because they treat every single pixel as a completely independent variable, ignoring the actual structure of human anatomy. The reality is, a cheek pixel and a chin pixel do not vary independently. They are strictly bound together by the anatomical structure of a human skull. Because of this biological constraint, that massive 65,000 dimension matrix is filled with an enormous amount of redundant, correlated data. Our objective is to mathematically isolate only the most defining structural features of the dataset without injecting our own human bias. To solve this, we rely on a mathematical framework known as Principal Component Analysis, or PCA. PCA allows us to parse this massive grid of pixels and extract the invariant directions of facial structure. By applying PCA, we abandon the naive basis of raw pixels. We transform our data into an orthonormal basis, revealing the hidden skeleton of the dataset. The first step is to abstract a physical photograph into a one-dimensional mathematical object. We do this by slicing the image into columns of pixels, stacking them end to end. A standard image becomes a towering column vector. We repeat this for every image, grouping these vectors side by side to form a massive rectangular matrix, our data matrix, X. Before analyzing the dynamics within this matrix, we perform mean centering. We calculate a single average face from the dataset and mathematically subtract that average from every column vector in matrix X. We do this because we do not care about the baseline characteristics of a human face. We only care about the variance, how each specific face mathematically deviates from the average. This document details the next step, using a covariance matrix to extract underlying structures and map out how those deviations relate to one another. We generate this matrix by multiplying our mean-centered data matrix X by its transpose, xt. Multiplying the m by n matrix against its transpose yields a densely populated square matrix. The sheer size is intimidating, but if we zoom in on a single intersection cell, the ijth element, its purpose becomes clear. That single element represents the exact variance between the ith pixel and the jth pixel across every single face in our dataset. This makes the covariance matrix a complete mathematical map of how the pixel space stretches, squishes, and correlates across human anatomy. To find the structural basis hidden within this map, we perform an eigendecomposition. When a matrix transforms data, it warps the space. A random vector gets knocked off its path, but rare specific directions remain fixed. We call these eigenvectors. While the space warps, an eigenvector refuses to tilt, staying locked on its trajectory. This geometric concept maps directly back to the facial dataset. An eigenvector derived from our covariance matrix represents a stable, recurring pattern of variance that persists across the entire dataset, regardless of individual differences. These eigenvectors capture the invariant features, like the consistent spacing of eyes or the angle of a jawline, forming the true basis of our data. Because our eigenvectors were calculated from an m by m matrix, every single eigenvector contains exactly m components, the exact same number of pixels as our original photographs. That means we don't have to keep these eigenvectors as abstract one-dimensional lists of numbers. We can fold them back into a two-dimensional grid. The visual result is the eigenface. It looks like a ghostly face, but is actually a pure visualization of a specific variance pattern. Not all of these eigenfaces are equally important. Each eigenvector has a paired numerical value, called an eigenvalue. This chart shows eigenvalues acting as volume knobs, dictating how much structural variance its eigenface captures. Large eigenvalues mean dominant signals. Small ones represent noise. By rank ordering them, we identify critical patterns and discard the long tail of low-variance noise. By keeping only the top eigenvectors, we have created a new, compressed orthonormal basis. We retained the structural essence of the data and stripped away the redundancy. Now we can put the system to work. Suppose we introduce a completely new, unseen target face that the system needs to recognize. We run a mathematical projection, passing the target face through our new basis of eigenfaces. Each eigenface acts as a distinct structural filter, outputting a specific coefficient, defining how strongly the target face aligns with that pattern. When the projection is finished, the output is no longer a massive image file, but a highly dense, short array of coefficients. This marks the change of basis. A subject is no longer defined by 65,000 arbitrary pixels, but by 100 structural coefficients. This radical compression is completely viable because the target face can still be reconstructed using a linear combination. The target face equals the mean face we calculated earlier, plus coefficient 1 times eigenface 1, plus coefficient 2 times eigenface 2, and so on. The computational reality between the old system and our new model is severe. Instead of laboring over 65,000 fragile raw pixels, the recognition system now runs distance metrics on robust vectors of just 100 coefficients. It identifies targets in milliseconds. By isolating the structural skeleton of the dataset, we replace raw pixel density with a compact, robust AI algorithm built on the math of human variation.